Welcome back to the channel. So in this experiment we are going to see the experiment number 4, that is program number 4. Implement time response specification of second order under damped system for different damping factors. So I have written the MATLAB code, that is numerator by considering 0025, denominator 165 at the time steps starting from 0 to 10 divisions, and the step size is 001, and figure displaying, hold on. So this omega n square root of denominator, the denominator 1 and 3 we are taking, that is 1 and 25. Then zeta value, that is the damping factor here, that is taken as denominator of 1 2 divided by 2 omega n. So like this we should start writing what is the system function. Transfer function is defined as omega n square 1 2 into zeta wn and wn square. So like this start writing. So here peak value, maximum value, settling time, okay, peak time, rise time can be calculated. So with the help of this mathematical calculation, so the transfer function we have taken here 25 divided by a square plus 6x plus 25. So we should compare this equation with the standard equation. The standard equation is this one, omega n square a square to zeta omega n s, and this is omega n square. So when you compare this, you can now look at this. Here s and s is there, 2 zeta omega n will come here, and the first one what we are going to calculate is natural frequency. So the natural frequency when comparison omega n square equal to 25, so omega n is 5 radians per second. So damping ratio, that is about zeta, this 2 zeta omega n compared with 6, so you will get here omega 1 value, you know, that is 5. If we substitute, zeta value will get as 0.6, that is a damping factor. So damping interval, damping natural frequency can be calculated by omega d. So that omega d equals to omega n, the formula is there, square root of 1 minus zeta square. So start substituting since you know the zeta value. So if I substitute here as 0.6, which I got from here, that is 0.6 from the previous stage, this one, right? So what you are going to get, you are going to get here omega d as 4, that is omega d means damped natural frequency. Then peak time can be calculated with the help of this formula, Tp equals to pi by omega d. So pi value if substitute, and omega d just you have calculated, just substitute, so you will get 0.7859 seconds, right? So rise time calculate, Tr equals to pi minus theta divided by omega d. So here pi value substitute, theta value substitute, and here zeta value if you substitute. So because theta equal to tan inverse of this value, so if I want to calculate this theta, substitute this zeta value, so you will get theta value after theta value. So if you substitute here, you will get the rise time. So similarly settling time is equals to 4 divided by zeta omega n. So here after substitution you will get settling time is equals to 1.333 seconds. So maximum peak overshoot, it is peak overshoot, it can be calculated as mp, that is e power minus pi zeta root of 1 minus zeta square. So substitute all here, so you will get the peak overshoot is 9.48 percentage, right? So if you execute here, the values are going to be like this. How? This is how it is going to look like. The values will come like this, right? Omega n, zeta, transfer function, theta, omega d, rise time, peak time, settling time, and peak overshoot. And the figure, since we have displayed the figure, that figure is going to come like this, right? So rise time, so it's a maximum peak overshoot and the settling time, right? So here we should execute this with the help of the MATLAB. Here I will close this, and here I will try to open the program, save it in some folder, then later you can just run this. After running this, you can able to see this execution, what is happening here. So starting with figure is also generated. So starting with this omega n value 5, zeta 0.6. So system function, that is a transfer function, continuous time transfer function like this, theta value like this, omega d, rising time, peak time, settling time, peak overshoot. So like this you will get the result. So it's a control system IPCC lab for the 4th semester ENC students of VTU, right? So I'll explain the next code in the next part. Thank you. This is the diagram of that is the experiment, the MATLAB code, amplitude, time. So here it is the rise, it is the peak overshoot, then it is going to be the settling time, right? So it is rising and it is reaching the peak, then the settling time. That's what the diagram will look like, the figure will look like for the 4th experiment. And the experiment name is what? The experiment name is, we are doing it for the second order. Why the second order? Because you can look at the transfer function, it is omega n square, right? So for that we are doing it, the MATLAB coding. So look at the implement time response specification of second order underdamped system for damping factors, right? So the damping factor, what is the value we have taken? 0.6. Like that, if you want to change, you can change the numerator and denominator and you can go for it. Okay, thank you.